Hi everybody, welcome back to the Feynman technique. Today, again, I'm going to be continuing the my tradition of doing these things kind of live and step by step in Desmos. This is another integral I got off the channel Maths 505, and we're just going to be solving it step by step. And I'm doing this from scratch, so let's get started. Well, kind of from scratch. I have done it before, but I'm not looking at any notes or anything like that. So, all right, what are we going to do first? I think the first obvious thing to do is make the substitution x is equal to arc tangent u. So dx will be equal to, it implies that dx is equal to 1 over u squared plus 1 du. So let's go ahead and copy our integral down here. All right, so our bounds are going to change. Okay, so that's going to be 1. This is going to be 0. So we're going to get 1 minus u. This is going to become a u. And our du is this. All right, and then I'm going to bring it back to x. All right, so now we have x, and then I'm just going to bring this down to the denominator, x squared plus 1. All right. Now what? Well, let's make a function of t like this. Let's see. We could put a t here, but then it doesn't converge, so we won't do that. So we'll put a t here. All right. So we just created a function of t. I just put a t right in front of that x right there. And now, well, pretty clearly f at 0 is going to give us 0. And f at 1 is going to give us back our original integral. All right, let's take f prime of t. That's equal to, of course, using the Leibniz rule for differentiation under the integral sign. All we do is pass the derivative inside the integral sign and take the partial with respect to t. So that's going to bring this down to the bottom. And then we will have a negative x. All right, we'll bring the negative outside. These x's will cancel. And we're just left with this. And then I'm just going to check to make sure I did the differentiation right. Put a little d dt in front of that, and I did. Okay. All right, so now what are we going to do? It looks like we're going to have to use partial fractions on this thing. I don't feel like doing that out. I mean, that's a pretty long, boring process. So I'm going to go ahead and pause the video, and we'll get the answer after I come back. All right. So after performing the partial fractions, I got that this, which is our integrand, can be written like this. All right. So let's go ahead and write that. So our f prime of t is now going to be equal to, let's see, negative integral 0 to 1 of our first term. But we can bring out this t over t squared plus 1, and then we'll just have x over x squared plus 1 dx. And right away, I'm just going to go ahead and put a 2 in front of there and bring a 1/2 outside. That way we'll have the derivative of our numerator, or our denominator in our numerator. And then let's see, it's going to be minus 1 over t squared plus 1 times the integral from 0 to 1 of our next term, dx. And of course, this is just pi over 4. So I'm just going to go ahead and write that as pi over 4 right away. So we're going to get pi over 4. And then minus t squared over 1 plus t squared times the integral from 0 to 1 of 1 over 1 minus tx dx. All right. And let's make sure these match up. They do. Okay, so now we can start working on this. All right. Well, let's see. Let's figure out what this is. All right. It looks like that's going to be natural log 2. But let's do it. Let's do it a little bit more thoroughly. All right. So we're going to let u equal x squared plus 1, implying du equals 2x dx. So there's our du right here, 1 over u, but our bounds of integration would change to 2 and 1. Yeah, that's natural log 2. So this expression right here, we'll copy it down here. And this is just natural log 2. So we'll put natural log 2 right there. And of course, well, this stays the same. Now for this one, we are going to let u equal 1 minus tx. No. Yeah. All right. Implying du is equal to negative t dx. All right. So du, so 1 over negative t du, or negative 1 over t du is dx. All right, let's change our bounds. All right, so if u is 1 minus t times x, that's 1 minus t. And then if u is, all right, well, that's going to be 1, right? Let me make sure I did that right. If u is 1 minus tx, we plug in 1 for x, so we get 1 minus t. Okay, so then if we plugged in 0, we'd get 1. So yeah, that's right. And this is just u. And our dx is negative 1 over t du. All right, so that is going to equal negative 1 over t times natural log of something minus natural log of something. All right, our lower bound is 1, so that is 0, it goes away. This is 1 minus t. All right, so that integral evaluates to natural log of 1, negative natural log 1 minus t over t. All right, so let's go ahead and copy that here, put it in a parentheses, and see if we got the right thing. We did. All right, so let's go ahead and distribute that negative sign outside. Let's see, this t cancels one of these t's upstairs, and now we have this. Okay, so f prime of t is equal to this. Now that doesn't look a whole lot better. It doesn't really look like we're going to be able to anti-differentiate. Well, we'd be able to anti-differentiate every term except for this. So what are we going to do? Well, let's recall back up here that f of 0 is 0 and f of 1 is I. So, and don't forget, this is the derivative. This is f prime of t. So if we integrate from 0 to 1 f prime of t dt, we will get the antiderivative f evaluated at 1 minus its antiderivative f evaluated at 0. F at 0 is 0, so that goes away, and f of 1 is I. All right, so if we integrate our f prime of t from 0 to 1 dt, we get I. All right, well don't forget, f prime of t is just this thing right here. So that is going to be equal to the integral from 0 to 1 of this dt minus pi over 4 times the integral of this from 0 to 1 dt times the integral from 0 to 1 of this dt. All right, but we're still left with this mess right here. All right, let's not worry about that right now. Let's go ahead and evaluate this integral right here. That's going to be pi over 4. So that's going to give us, maybe I'll go down one more. We'll do a step here. Okay. So this is pi over 4. That's going to give us minus pi squared over 16. Squared over 16. All right. This, I mean, that's an easy integral to evaluate. Looks like that's going to be maybe natural log 2 over 2. Yeah, it is. All right. That one is natural log 2 over 2. So that's going to give us natural log squared over 4. All right. So copying this down here, we have I is equal to this. And we also have I being equal to this. All right. So I'm going to change the dummy variable here back to x. All right. Well, we have two different expressions for I. So we can add these two together. All right, so if we add the left-hand side, we get 2i. And if we add the right-hand sides together, we get this plus this. Okay. Well, here, look what we can do. Let's multiply the top and the bottom of this by x. So we get an x squared upstairs now. And now we have the same denominator in both our integrals right here. That means we have the same bounds of integration too. So that means we can just add them together by adding their numerators together. So let's copy this over here. Say plus this, and now we can get rid of this. And I'm just gonna do a quick check here to make sure we're on the right track. I'm gonna put a parentheses around here and divide both sides by 2. All right, yeah, we're on the right track. Okay, so let's put it back. And now what can we do here? Well, we have a common factor. We have natural log 1 minus x is a common factor of this numerator. So let's go ahead and factor it out. That's going to be a 1, going to be an x squared, and then I'll put it at the end. There we go. Okay. And now you'll notice that this and this cancel. This is a well-known integral, and I've shown it here before on this channel. I don't want to go through the process of showing that. I believe that is negative pi squared over 6. Let's see if I'm right. Let's see, negative pi squared over 6. It is. All right, so we're done. 2i is equal to this plus or minus pi squared over 6. And let's see, dividing both sides by 2, we get this. This becomes a 32. This becomes a 12. Yeah, that's it. So that's the answer. Let's clean it up a little bit. This can be expressed as, I believe, 3 over 96. And this would be, let's see, 8 over 96. No, hold on. How many times does not 12 go into 96? Yeah, 8. 8 times. Okay, 8 over 96. All right. So that is going to give us negative natural log squared of 2 divided by 8 minus 11 pi squared over 96. All right, guys. I hope you enjoyed that. We'll see you next time.